And so we continue with the electrostatic force. We'll do 3 problems. I'm going to do the following in your textbooks. On page, this is page 681, so 681, I'm going to solve problem 52. And this one has, this one has 5 bars. So this one has 5 bars, and so presumably it would be hard. It's a little tricky. This is what I'm going to solve with you. And then you guys will do, I think it's on the next page, so page 682, you will do problems 53 and 54. And I don't remember exactly what these two were about, but I kind of remember that they were difficult for the students. So you can expect these two to be hard. I'm gonna turn this into your homework. So this is your homework. Alright, so I'm gonna solve problem 52 with you now, and then you will try 53 and 54, submit whatever you've managed to do. Problem 53 has an answer in the back of the book because it is an odd problem, so you can check if what you did is correct. For problem 54, you don't really have an answer in the back of the book. And then I think what will happen is when we come back to school, I suppose next week, it'll be a while, I'll go over 53 and 54. That might actually be a good review to get back into the swing of things after about a week of not doing physics. So anyways, 52. Alright, let me draw a picture for 52. You can pause the video now and then read the problem. The picture runs like this. You have a positive charge, and let's label this as Q1, and this charge is 2 nanocoulombs. So this is 2 nanocoulombs. Then you have a negative charge here. Let's label this as Q2, and this charge is 4 nanocoulombs, but it's -4, so it's -4 nanocoulombs. And then remember that nano is 10 to the -9th. Now the distance between the two is given to us. We will need the distance, so maybe I'll put it somewhere. Maybe I'll put it here. The distance between them is, I think, 1 centimeter. Let me double check. Yeah, it's just 1 centimeter, so 0.01 of a meter is the separation between the two charges. Now the question is, where should you place a positive proton so that it experiences net force of 0? In other words, you want equilibrium for a proton. Now the reason why this problem is tricky is because you kind of have to visualize what's going on first before you can set up your equations. So suppose you place a proton somewhere here, kind of like what we did with the other problems in one-dimensional equilibrium situations. Let's say we place this positive proton here, and then we try to figure out where should it sit so that it's in equilibrium. Well, there's a problem. You can't place this positive charge in the middle. So again, the problem is, where should you place it so that it's in equilibrium? But you can't place it in the middle between the two, because the first force between these two is repulsive. So it points in this direction. This would be your F1. And the second force between these two is attractive. So it would also point in the same direction. This would be your F2 due to Q2. Right? So anywhere you place this proton, if you were to place this proton anywhere between these two charges, the forces wouldn't cancel out. It would be impossible for the forces to cancel out. So you can't place the proton in between the two charges. So I'm going to get rid of all of this. Now let's say you placed it here. Right, because the only other options that are left is either place it here or place it here, or in the middle. But in the middle we can't do that. That's not going to work out. So let's say we place it here. Well, then let's see what happens. We have force between these two, which is attractive force, and that force F2 would point like this. It's an attractive force, so here's F2. And then you have a force between this one and this one, which is a repulsive force, and then this one would point like that. and this would be F1. So they point in opposite direction, so that's promising. But note that the distance between these two is smaller, and this charge is bigger than the other one. So since the equation is F equals K, Q over R squared, if the distance between these two is smaller than the distance between these two, then that makes this force bigger. But also this charge is bigger, so it still makes this force even bigger. And so this force would always have to be bigger than the second force, and the second force would always have to be smaller than the first one. So I want to draw it even smaller. Anywhere you place this charge here along to the right of Q2, F2 would always be bigger. So it's not possible to get an equilibrium if you place this charge here. Again, look at this equation. Distance between these two charges is always smaller, and this charge is always bigger than that one. That implies that this force would always have to be bigger than that. That means you can't place the charge to the right of Q2. So the only place left would be to place it somewhere here. Alright, so let's clean this up. So we can't have it here. That goes. Now we have speculated that the only place that we could put this charge in is here. Let's see if that actually makes sense, because maybe it's not possible, and so that maybe it's just not possible to get an equilibrium. So let's see if this location makes sense. So let's say I place the proton here, then I get a repulsive force between these two, and that repulsive force would point like this. Let's call it F1 because it is due to Q1, and I'm going to get an attractive force between this and that, and this force points in this direction. Let's call this thing F2. Now the equation for the force is F equals K Q over R squared, and what I get is between these two the distance is smaller than between the other two, but this is also a smaller charge, so it's at least possible that I should be able to obtain a situation where this force is equal to that force, because even though the distance here is smaller, this charge is also smaller in magnitude. So the only possible location is to the left of Q2. Then I can get an equilibrium. Alright, so what I need is a distance here. This is what I'm after. Why don't I call this thing X? I'll call that X, and it is X that I'm after. So now let's set up the equations. F1 equals F2. I want the equilibrium. And now F1 would be K. Charge of a proton. How should we do this? Proton charge Q. Let's just say Q is going to be the charge of a proton, which is 1.6 times 10 to the minus 19th. And then we have Q1 and we have Q2, but this would be Q here. So I'm going to put Q. So I'm going to have F1 is Q times Q1 over X squared, and this equals KQ times Q2 over X plus 0.01 squared. Alright, now things that cancel out. So K goes, Q goes, so it doesn't really matter that it's a proton. And then let's plug in the numbers. Maybe we can cancel a little more. So Q1 is 2 nanocoulombs. Oh, actually we can cancel. Okay, good. So I'm going to get 2 times 10 to the minus 9th over X squared equals, and then here I have 4 times 10 to the minus 9th over X plus 0.01 squared. Now what cancels out nicely is the exponent here, so that goes away. I can also simplify my life a little because this can be 1 and this could be 2. And so now I have a relatively simple algebraic expression where I have 1 over X squared equals 2 over X plus 0.01 squared. Alright, so let's finish this. Let's move it up here. Cross multiply, so 2x squared equals x plus 0.01, and square this thing, take the square root of both sides. Square root of 2 is I think 1.4. Let me double check that before I write this. Yeah, alright, so 1.4 times x equals x plus 0.01, and that gives me 0.4 x equals 0.01, and so x equals 0.01 divided by 0.4. 0.01 divided by 0.0, no, not just 0.4, I get 0.025, so this is 0.025 of a meter. That would be the answer. That's the same thing as 2.5 centimeters, and that's probably what's listed in the back of the, actually it's not, because this is an odd problem, an even problem. So anyways, this is the answer. We found the x is 2.5 centimeters. That was problem 52 on page 681. Yours are these ones here. All right, number 53 and 54. And like I said, they're both hard, or at least students tend to find them hard. And for problem 53, you have the answer in the back of the book, so you can double check that, see if that's correct. Next time you're in a class, next time we meet, I'll probably go over these two, and then we'll keep moving forward. Friday is off, so I won't see you Friday. Okay.